Okay, let's record to the cloud. So that is now happening. And so welcome to you all once again, and to this first in a little series of talks about physics and the basic principles of it. And I think Western science really and physics can be pretty much said to have started in the round about the 1600s with these various people, who I hope you now see on the screen. As you can see, dates all sort of sloshing around the 1600s. And that was when I think Western science, as we now know it, got going. I'll come back to that in a moment, but let's start now by thinking where we will get. Sorry, I'm just playing with a thing and I'd rather lost the track. Right, so then, yes, Western science got going in about the 1600s, initially really with consideration of motion. Up until then, broadly speaking, I suppose, from Aristotle and goodness knows who others, there was a more sort of, I don't know, metaphysical view of things that, for instance, objects, if they were moving, usually stopped. And that was because the natural state of things was to be at rest. And things usually fell if you dropped them because the sort of natural state of objects was to be near the center of everything, which was the sort of center of the earth. And the behavior of things in the heavens, you know, the sky, the stars, the planets, the moon, the sun, that was a completely different realm. That was the heavens, where everything was perfect. Whereas on Earth, everything was mucky and nasty, and you really had hardly any idea what was going on. Those were the sort of views that were prevalent. But in these 1600s, they were beginning to be addressed in a different way. People obviously must have recognized that there was a fairly high degree of orderliness in nature, in as much as there was a strong relationship between how hard you threw something and how far it went. And in fact, it must be a pretty good relationship, because people who are really good can work out exactly how hard to throw something to get it to go more or less exactly where they want it to go. So there is an orderliness, but how can one sort of characterize it and parameterize it? This was perhaps the way people started to move in these periods. How far something goes depends on how much of a sort of push or pull you give it. Can one sort of measure how much push you're giving it? Well, old Robert Hooke said, well, yes, you can measure a force, can't you? Because a spring, the more you pull it, the further it goes. And in actual fact, if you pull it twice as far, it exerts twice the force. And so he came up with, now I hope you can actually see this, I'm just to check myself, and I'm going to get myself into speaker view, which is supposedly me. Can you actually hear anything at all? Good, I hope so. Right, well, speaker view seems to have gone mad. But at any rate, Hooke's law, if you like, was something like this, that the force being exerted by a spring is a constant times the extension of that spring, how far you've pulled it from its normal position. You pull it twice as far, you get twice the force out of it. And that was really one of the very earliest little actual mathematical laws about how things work. It allowed one to characterize a force. Then what about this idea of motion, and that things just come to a natural stop? Well, the view people like Galileo and Newton, by careful experiments of balls rolling on inclined planes and things like that, came to the conclusion that actually, no, the reason that the ball stopped moving was because the plane that it was rolling on was very slightly inclined and it was going upwards slightly. The more level you made it, the further the ball went. And they began to think, well, if it was perfectly level and perfectly smooth, presumably it would go on forever. And therefore came to the view that actually things don't naturally stop. They actually stay doing whatever they're doing, moving or stopping, unless one of these mysterious forces acts on them. And in fact, one can characterize, again, the amount by which the velocity of the thing's motion changes, the acceleration of it, the rate of change of its velocity is equal to the force applied. Twice as big a force, twice a big acceleration. Another factor comes into play, what earlier was called inertia, the sort of resistance of something to movement. But Newton realized that this could be more tied down as being the mass, very closely related to the weight of an object, how much stuff there was. The more stuff there was, the harder it was to accelerate it. So the equation becomes this. The acceleration you get, the change in velocity per unit time, is proportional to the force, twice as much force, twice the acceleration, and inversely proportional to the mass. If it's twice as massive, you get half the acceleration out of it. So this was the next sort of little mathematical expression relating things like mass, force, acceleration. One needs to point out that this acceleration is the change in velocity, which has direction as well as value. So it's not just pushing something in a straight line and making it go faster. Another sort of change in velocity is if something's moving in a circle, like a conker that you're whirling around. Oh, people, you can't see that, thank you. Yes, right. So if you're whirling a conker around your head, there is a force acting inwards to keep it going. If you let go of the string, it flies off in a straight line. But as long as you hold on to the string, you are changing its velocity, because one moment its velocity is like that, the next moment it's like this, and when it's here, it's like that. So the velocity is changing. That is an acceleration, and it's being provided by this force here. So that's an important factor, that velocity and acceleration are both have direction as well as value, as does force. Okay, well, that was the next little equation. So this is beginning to get hold of how things behave when forces are applied to them, but it doesn't quite get to the bottom of how far things go when you throw them. It's not just a matter of how hard you push, is it? I mean, golfers will say that it's important that you follow through. Well, what on earth does that mean? What's all that about? It turns out, and this is now moving on to the discoveries of, shortly afterwards, as all of this was being put together, it turns out that in nature there are two very important developments of the idea of the force. There's the force times the distance that it moves through. That is known as the work done. And that turns out to be a very significant way of working out exactly what a force actually does, how it changes things. The other thing that's important, so this is the work, the other thing that's important is the force times the time that it acts on, and that's known as the impulse. Now, what do these things mean? Well, the work done turns out to change the energy of an object, which, now I won't go into proving this as that's a bit laborious, but the energy of a moving object is given by this little formula. It's getting a bit more mathsy now, isn't it? Oh gosh, mass times the velocity squared half. Now that is what's known as the kinetic energy of an object, and that is what is delivered to it if this amount of work is done on it. So the bigger the distance that the force acts through, the bigger the amount of energy that you get delivered to the object. This impulse affects what is known as the momentum, which is just mass times velocity. The longer the time, the bigger the velocity, so the more momentum the object has got. And those two concepts turn out to be very important and useful in determining how things behave. And I think the point I should be making is that they're slightly weird. I mean, what actually are they? Very good question. They turn out to be useful ideas for sort of analysis and gaining a prediction of what's going to happen. But what they actually are is rather strange. It turns out that this energy thing is actually conserved, meaning that you don't change it, you don't create it or destroy it, you just change it from one form to another, apparently. Well, now, that sounds initially a little bit dubious, doesn't it? I mean, if I throw a ball up into the air, as it leaves my hand, it's got a lot of this kinetic energy. But as it goes up into the sky, it slows down and down and down until eventually it stops. So it's lost all its kinetic energy, hasn't it? So it's gone. Ah, say the physicists. So no, it hasn't. It's turned into potential energy by virtue of its greater height. Well, but I mean, that's just a mathematical fiction, isn't it? I mean, there isn't really such a thing as potential energy. Well, this is the point, isn't it? It turns out that it works beautifully. It always does. If you drop something from this height to that height through a distance h, it always gets the same amount of kinetic energy at the bottom. So by raising it up that height, you have indeed, or at least it works if you say that what you've done is given it some more gravitational potential energy. There are various other forms of energy, heat and chemical energy, like they say on the back of a Mars bar, you know, energy 1.2 megajoules or something enormous. That means that if you combine that Mars bar with oxygen, you will get 1.2 megajoules of energy out of it, which in principle you could use to fire a cartridge to accelerate something away with the energy becoming kinetic. But this, and I think I don't want you to sort of get too agonized about this. I think the point I'm making is that this strange concept of energy, which you might say, well, what actually is it then? If it can be heat and it can be motion and it can be height and it can be chemicals, what is it? Well, we don't really know, but it's just a very useful idea for calculating things and doing things. And this conservation seems to be a completely inviolate rule, such that various times later on in physics, when something has happened which people think it looks as though it's violated the law of conservation of energy, other physicists will say, well, it can't do. So in that case, there must be something else that's happened which we can't see, but which has taken that energy away. And that approach has always worked. It's turned out, yes, there was a particle which we haven't detected that took the energy away. Yes, it works. Always works. Never failed once. This momentum is another strange thing. it also is conserved, but it's conserved in a different way. Whereas you can't create energy, you can only transfer it from one form to another. Momentum you can create, but because it has direction, it's something times the velocity, it has direction. If you create momentum in this direction, you always find that you've created an exactly equal amount in that direction. So it's conserved in that sense. Positive momentum this way is always balanced by an exactly equal amount the other way. That's what is another consequence of Newton's third law about actions and reactions. And that also turns out to be a very useful phenomenon. I'll just describe an application shortly, but what momentum is. I always remember a friend of mine at Oxford when he was teaching, whilst he was trying to do his PhD, he was teaching at a girls' grammar school, and one of the girls there asked him, "But sir, what is momentum?" And he said, "Well, it's product of mass times velocity." "Yes, but what is it?" "Ah, yes, what is it?" "Well, yes, it's sort of it's not energy. And I feel it's sort of how hard it is to stop something. A bullet has got a lot of energy because it's got a lot of speed, a lot of velocity, not much mass, but it's still, the energy it's got is very large. So when a bullet hits you, it does lots of damage. But if you shoot an elephant, you might smash its skull up, poor thing, and do all sorts of stuff, but you won't stop it. Won't make any difference. It's got no momentum, really. An example of something that's got a lot of momentum but little energy is something that's got an awful lot of mass but not much velocity. And a good example, I think, for those who are familiar with our church at St Andrews, is one of those stacks of triple chairs, of about 25 triple steel chairs on a trolley. Once you've got it going, it takes an awful lot of stopping. And if you were standing casually on the floor of the church with this thing trundling at you and it bumped into you, well, it wouldn't tear you limb from limb or cause an awful lot of damage, but it would jolly well push you over. You couldn't stop it. Oh gosh, and that's sort of thing, like that's momentum. Whereas a bullet is a good example of energy. And the consideration of the two is quite significant. I think one thing, and this was something that was pointed out to me at an interview at the Royal Aircraft Establishment when I applied, and the chap asked me this question, and I couldn't answer it, and he explained the answer, and I thought, oh goodness me, I never realised that. How most interesting. Because with motion, because of the law of conservation of momentum, as you try to move yourself one way, you always have to move something else the other way. As I walk along, I'm actually slightly pushing the earth backwards. But of course, because it's so absolutely enormous, you don't notice any difference. But with an aircraft with its jet engine, of course, it works by blowing air out backwards, which pushes the aircraft forwards. And the fuel that's being burned in here, if you can see that, the energy that's released by burning it is always divided between what's going backwards and what's going forwards. And because of that half mv squared bit, what's going away at great speed is actually taking an awful lot of energy away. And so the earlier jet engines that threw out air at a huge speed were actually hideously inefficient, because most of what you wanted, i.e. the motion of this aircraft, most of the energy of the fuel was going into throwing the air out the other way. You couldn't not do that because you always have to balance the momentum. But if you're trying to move something with an enormous mass by throwing out very little mass, you end up having much more velocity there than here, and much bigger energy. So more modern jet engines, you may notice they tend to look more like this now, have a sort of shrouded fan and not just the little tube there used to be. They are more efficient because they push out a bigger mass of air at a slower speed, which means that less of the fuel burn energy is going into the wasted chucking the air away, and more of it ends up doing what you want, i.e. having the aircraft move this way. And when the chap explained that, I thought, oh no, he asked me why do they have these high bypass, and I muttered on about heat or something. And then he explained, and I thought, oh, that's interesting. I didn't realise that. I never knew that. And, you know, this actually came out of thinking about that. I'm never sure that the people at the sixth form college when I used to expound it actually thought it was very interesting, but I did, so they're all idiots. Right, that I think is where we've got to on motion. And as I say, the main thing I wanted to stress was that what led to a greater understanding and way of coping with these things was concepts, things like force, mass, momentum, energy, work, funny things like that. And I used to think at the sixth form college, when we were told that most jobs that people are going to be doing in 10 years' time don't even exist now. So how on earth can any education prepare people for the world? I used to think, well, the only thing that physics might offer is familiarity with strange abstract concepts. That is perhaps an ability which you get from doing physics, which might possibly be useful in later life. And I suppose in a ghastly way, it shows to be a bit in terms of all these people working on financial derivatives and goodness knows what, because a lot of them turn out to be physicists, apparently. Physicists are in great demand by Citibank and all the rest of them. So that was what I feel they brought to the table. Now then, time ticks on. The other thing I would like to address is gravity, and this was Newton's other great big thing, of course, how his really investigations into gravity. Now, how did all that work? Well, this is a bit of a saga, but I think I'd like to go through it. Lots of people by this stage had been making very painstaking observations of the planets and realized that actually, although we now realize they moved around the sun, they didn't actually move in perfect circles. They moved in ellipses like this with the sun. I mean, that's exaggerated. They're very nearly circles, but they aren't quite. And the sun is at one focus of the ellipse. And this describes the orbits of all planets. And the question is, what could actually make them move like that? You can't, by conquer twiddling example, you can make something move in a circle, but you very well can't make it fly in an ellipse. It requires a very much more complicated sort of force to get it to move in an elliptical motion like this. How can that work? So Halley, of Halley's comet fame, came along to Newton and said, you're a mathematician, or at least you're clever. What sort of thing would create elliptical orbits like that? And so Newton more or less invented the mathematics to show that actually, if you had a force which was proportional to, and just something over that distance, I'm going to call big R. If you have something which is inversely proportional to the square of the distance, that works beautifully. So in other words, if whatever this force is gets 4 times weaker if the distance between the two relevant objects is twice as large, that works like a charm, and you get this elliptical movement. And it wasn't a completely way off thought, because other things that we know about fall off as the square of the distance. Light, for instance, a light that's twice as far away is 4 times dimmer. Sound in the open air, twice as far away, 4 times weaker. So it wasn't a completely weird idea, but Newton really, with his new mathematics of calculus and all sorts of other clever stuff, came up with this. But the question was, what was this weird force? And then the apple story, I think, is really sort of encapsulating the big step that Newton made by thinking, well, something is attracting this apple onto the ground. Is it the same thing that's attracting the planets around the sun? Is it not a case of a different realm up in the heavens to down here? Is it all the same? Well, we can work it out. And this is where, of course, the old sort of scientific approach, we can test it, he said, because we know that the moon, trundling round the Earth, is moving in, well, pretty nearly a circle, which we can work out from the old force is equal to mass times acceleration. We can work out from the length of time it takes to go round and the distance, we can work out what the acceleration inwards is that is needed for the moon to go round at that distance and in that time. And so I'll call that GM for moon. And we know what the acceleration is of something that's dropped on the surface of the Earth. We know that's GE, I'll call it. And we know what the radius of the Earth is. The clever old Greeks worked that out. Now, I suspect that might be familiar to many of you, but they actually were a very ingenious lot, the old Greeks. And they worked out, you may have come across this, that basically somebody observed that at a particular time of year, must have been in midsummer in the Northern Hemisphere, the sun was directly overhead at a point down in the Sahara Desert. But at the same time, in Alexandria, it never got overhead. There was always a shadow. And so the Greeks realized, well, if this angle, say that the sun gets to is a tenth of a right angle, then this angle must be a tenth of a right angle. And so this distance must be a tenth of that quadrant. So if we can measure this distance, we can work out what the circumference of the Earth is, and then being Greeks and knowing all about pi and r and stuff, we can work out what the diameter is. Aha, aren't we clever? And they jolly well did. It was a bit difficult to work out that distance. That apparently Eratosthenes had to pay somebody, basically people who were good at doing that sort of thing, to walk it with standard paces, 5,000 paces or something, you know. So it's quite a long trek. But anyway, they measured it out and he got it pretty nearly right. So they knew the diameter of the Earth. How did they know the distance to the moon? The old Greeks, clever stuff. Can you see this all right? I think I'll keep it like that. So what did they do? Well, they observed that when you get an eclipse of the moon, you can see the shadow going across it is sort of curved. And so they thought, oh, well, in that case, presumably the Earth, if it was that as far away as the moon, would look like that, wouldn't it? And we know how big the Earth is, so if it looks like that and we know how wide it is, we can work out how far away it is. And now, what was the name of the chap who did that? Hipparchus. Sorry, I should have to check my little notes. Where are we? Hipparchus, that's right. Hipparchus sussed this in 150 BC. And again, he was pretty well right. So Newton knew what this was, this distance to the moon. He knew what the radius of the Earth was. He knew what the acceleration given to things on the Earth's surface was. He could calculate what the acceleration needed to get the moon to go around the Earth at the distance it was. And lo and behold, the two accelerations were indeed in the ratio of this squared to that squared. So gravity obviously does apply both on the Earth and in the heavens. It's actually not a case of one rule for them and one rule for us. We're all in it together. It's all the same. The whole universe is subject to what we then came up with as a universal law that any two objects experience a force which is dependent on the mass of the two objects, the mass of the little object, mass of the big object, divided by the distance between them squared. And now there needs to be a constant here because, of course, this depends on, and what do you measure that in? Tons, ounces? What's this? Miles, meters? So there needs to be something here which effectively represents the force that you get for unit masses at unit distance apart. And in physics units now, the unit of mass is the kilogram and the unit of distance is the meter. So what force do you get between two objects of mass 1 kilogram a meter apart? And the answer is something extremely small, 10 to the minus 11 in math speak, which is very nearly, well, it's 1 divided by 12 noughts or 11 noughts. So in other words, it's a very, very small number. The gravitational force between two ordinary objects is pathetically weedy. Gravity is a very weedy force compared to some of the other ones you find in the universe. But this was really Newton's big step to realize that there is a fundamental universal law that applies as far as we know right across the universe, and that's it. Now, the interesting thing in a way was that at the time, that wasn't really considered to be a proper explanation because it doesn't say why, it just says there is with a bit of formula. And some people like Kepler and others were a bit dismissive of this idea of attraction. What, do you mean they fancy each other? I mean, literally, because that was the word that was used, an attraction. It was thought to be a sort of, you know, love between the objects. Well, I mean, Newton said, obviously, this is a rather silly suggestion, but I leave further investigation of it to the reader. And what is interesting is that since that time, really, what one might call the mathematical worldview has moved in. As we found more and more that we could use these mathematical techniques to understand what's going on, and we, the instruments that we developed, you know, telescopes, microscopes, oh no, where's the shared screen thing gone? Ah, yes, I'm just going to turn back to these people for a moment. These people here, the combination of the scientific method effectively developed by Bacon, the idea of taking lots of observations and trying to induce principles from it, and the mathematical approaches of Galileo and Hooke and Newton and others led to an enormous expansion of our knowledge of the universe, a quite amazing expansion of our knowledge of the wonders of the universe, the size of it, the scale of it, the amazing complexity of life. All sorts of things have been opened up to us by this scientific method. But at the same time, it also could be said to have resulted in a very considerable narrowing of our vision, such that we've come to the view that anything which isn't susceptible to the scientific method, anything that isn't completely predictable, anything that isn't actually ultimately expressible as in a mathematical form, can't exist. It's not there, because if we do a scientific experiment, it won't show up. So therefore, what you might call anything like the spiritual dimension of reality, anything like God, or anything, well, of course, that can't be there, because we can't measure it, and it's not mathematical, so it can't exist. Simple as that. That is the mathematical mindset that has become quite prevalent. I was interested in this idea that Newton and others at the time of his equation didn't think that was a proper explanation, because certainly by the time I was teaching this at the sixth form college, that was considered a completely full, perfect and sufficient explanation and satisfaction for everything. All you do is say, this is Newton's law of gravitation, gravitational constant, mass, distance between the two. That's it. That's it. What else is there? The mathematical expression had become a completely satisfactory explanation. And that, I think, is the sort of the downside of the triumph of maths in scientific understanding. It has, I argue, has this narrowing effect. And I think, time permits, I think I would like to read something from this book, which I don't know whether you can see, by quite a renowned physicist, Carlo Rovelli. The reality is not what it seems. It's a jolly good book. I mean, it's all about physics, and he puts it very well to get across the subtleties of loop quantum gravity and goodness knows what in ways that one could just about understand. But when he gets on to non-physics, it gets much flakier, and it's greatly ironic that his description at the end, he is absolutely in that he's just as bad as the people he castigates. And I think I'll read this bit because it's very rude about religion and things. And it shows that his mind is completely closed, absolutely shut in. The only thing that we have to do is to refine our mathematics, because there isn't anything else, because there can't be. Well, because there just isn't, it's obvious. Ignorance can be scary, he says. Out of fear, we can tell ourselves calming stories. Up there beyond the stars, there is an enchanted garden with a gentle father who will welcome us into his arms. Doesn't matter if this is true, it is reassuring. There is always in this world someone who pretends to tell us the ultimate answers. The world is full of people who say that they have the truth because they have got it from the fathers. They have read it in a great book. They have received it directly from a God. They have found it in the depths of themselves. There is always someone who has the presumption to be the depository of truth, neglecting to notice that the world is full of other depositories of truth, each one with his own real truth different from that of the others. There was always some prophet dressed in white, brackets a white lab coat perhaps, uttering the words, "Follow me, I am the true way." I don't criticize those who prefer to believe in this. We are all free to believe in whatever we want. But for my part, I prefer to look our ignorance in the face, accept it, and seek to look just a bit further, to try to understand that which we are able to understand. to seek to go further seems to me to be one of the splendid things which gives sense to life. I'm skipping a bit here. As Dante's Ulysses reminds his companions, we are not made to live like brutes, but to seek virtue and knowledge. The world is more extraordinary and profound than any of the fables told by our forefathers. I want to go and see it. To accept uncertainty doesn't detract from our sense of mystery. On the contrary, we are immersed in the mystery and the beauty of the world. The world revealed by quantum gravity is a new and strange one, still full of mystery, but coherent with its simple and clear beauty. It is a world that does not exist in space and does not develop in time, a world made up solely of interacting quantum fields, the swarming of which generates through a dense network of reciprocal interactions, space, time, particles, waves, and light. A world without infinity, where the infinitely small does not exist, because there is a minimum scale to this teeming, beneath which is nothing. Quanta of space mingle with the foam of space-time, and the structure of things is born from reciprocal information which weaves the correlations between the regions of the world. Now, here we go. A world which we know how to describe with a set of equations, perhaps to be corrected. It's a vast world with still much to clarify and explore. My fondest dream that someone, one of the younger readers of this book, I hope, will be able to voyage across it and illuminate it better. Beyond the next hill, there are worlds still more vast, still to be discovered. So he likes to portray himself as the great adventurer, open to everything. But he's not open to everything. He's only open to maths. That's all he can see. His universe consists of nothing except what is quantifiable by mathematics. He might not say that he was the truth, because he says, no, we've still got some more maths to work out. But what he tacitly is saying is, but we know the way, the only way in which everything that is worth knowing can be known. There isn't anything else. I saw a nice little quote which said by Arthur Schopenhauer, which says, every man takes the limits of his own vision for the limits of the world. Well, that is exactly old Carlo Rovelli, I'm afraid. And that, I think, is an interesting little sort of sense emerging from the mathematical worldview that we've generated for ourselves. Right, well, the last thing I just wanted to mention, but I won't go into any great detail of it, but just to note, is that going back to these people, you might wonder who on earth is Archbishop James Ussher? What did he discover? Well, he was the chap who came up with the great 4004 BC date of the creation, based on going back through the Bible and totting up all the ages of the people in Genesis, and then totting up the reigns of the kings, and finally getting up to when Israel was sent into exile, and that linked up with the Babylonian king whose dates were available from Greek and Roman sources. So he could put it all together and get this date of creation out. And I just wanted to note that, interestingly, you see, he was at just about the same time as some of these others. In other words, that whole view was all part of the sort of new approach of trying to apply measurement and numbers and maths to things. And whereas it worked fine for the natural universe, perhaps it wasn't quite appropriate for things like the Bible, which maybe was behind perhaps why it doesn't come out quite as well. Although somebody did actually remark that 4000 BC is about when most civilizations across the world, the so-called axial ages, about when most civilizations, India, China, Mesopotamia, all started about then. But at any rate, I just thought that was interesting to note that he was one of that gang. Right. that is, you'll be vastly relieved to hear the end of that.